All right, welcome back, everybody. If anybody's out there, so I could use the Ethernet cable if anybody's back there in the booth, but somehow my Wi-Fi is not working again. Okay, so today we're transitioning into perception. So let me, even just as a quick setup, right? Last time we built an almost complete manipulation system, if you will, right? We had our hardware abstraction, our hardware simulation. And we built on top of that our differential inverse kinematics block, which, well, after some integration, sent us EWA commands, EWA positions. The diff-ik block needed to know the current EWA state. So we had an important line here. Okay, but the whole thing was predicated on something over here, which just had a gripper velocity trajectory coming in. Okay, and although that's a complete closed loop system, hidden inside when we designed the gripper trajectories and then differentiated them to get the gripper velocities, we made a big assumption, which is that we knew where the red brick was, okay? So everything was sort of based on this, someone told me exactly where in the world I needed to reach to, and that's just not good enough, right? At some point we have to now use our sensors to figure out where the brick is to do the work. So far we assumed a perception oracle, right? Someone you could just query and tell us where the object was in the world frame. And we were using some of the cheat ports, like we could tell the body pose directly of any object in the world, right, in our hardware station. And so the goal today is to stop using those cheat ports and start using cameras instead and close the simplest loop we can around that whole system that could actually be run on a real robot. So I'm going to download a ridiculously big Meshcat animation over my phone's 5G and burn my data plan for the month. But hey, here we go. It's ridiculously big just because the YCB objects, if you know what these are, this is a mustard bottle from the YCB objects, okay, database. It's a little funny here, okay. The meshes, or the material files, the texture maps for these files are like 50 megabytes. So it takes a minute to download. Okay, so this is roughly what we're doing. Almost the same as what we did last time. The big difference is that we're going to have cameras now in the scene. These are cameras. I brought some. I don't always have cameras in my pocket, but today I do, okay. Yeah, they're like this, okay. This is the 415, this is the 435, RealSense cameras, okay. Super, you just USB plug them in, and you're good to go. They're amazing depth cameras. I'm going to tell you a little bit about them today, okay, what's going on here. But that's what you see in the scene are these depth cameras sprinkled throughout. A bunch of them, actually. We put 3 on each bin. You'll understand why. Okay, and then mostly this is just the same kind of thing we did before, where we start off, we figure out where the mustard bottle is. That's the role of perception. We do our standard gripper trajectory and make our move from part A to point B. Now, what the heck is this thing that's getting left behind? Okay, that thing is a point cloud, which is computed by reading the cameras at time 0, okay, and doing some initial processing on the data that you get back from those cameras in order to make the decision about where to grasp, okay? So at the moment of perception, I went ahead and put those in. Okay, I have observations like this, and then I have a model of what I expect those observations to be, and they end up matching. Okay, and we'll do all that by the end of the lecture. Okay, so we're going to think in terms of these point clouds today. Okay, so, oh no, not again. All right, so like I said, today is the first day of perception. We're going to do a lot of perception throughout the course. Today is kind of the more geometric view of perception. We're not just learning a deep network that goes from image to whatever representation we want. We're going to start by doing the geometry version. Now, even though going from image through a deep network directly is, I think, by all accounts, the best way to do things today, there's still a lot of perception tools that have baked in them, whether they're neural network or not, some of the fundamentals of geometry. It builds beautifully on what we did last time, I think, in the kinematics. Okay, and if you're interested in ideas like neural radiance fields or baking 3D priors, geometric priors into your neural networks and everything like this is going to be the foundation you need to do that kind of work. So today it's a slightly old school version of perception, but it's the foundation. Okay, so we'll do incremental, iterative closest point. Yes? We'll talk about where NERF comes into the stack later. Yep, there's places where it makes a lot of sense. Okay, so everybody knows about the deep learning revolution. I think a few less people realize how much of a geometry revolution we've had at the same time. Okay, and it was powered partly by deep neural networks, but even before that, it was powered by, I don't know, autonomous driving companies really caring about where the pedestrians were in the space, people building a lot better sensors. I mean, virtual reality and augmented reality were a big driver too. Okay, and we started getting pretty incredible things that had no neural networks involved. Okay, this is even, I don't know, 8 years ago or something like this, dynamic fusion, where we started having algorithms that could run in real time and build instantaneous 3D reconstructions of the perceptions they were seeing and track, people moving around, building sort of these beautiful 3D models. And that was a culmination of algorithmic work, of new sensors, and in particular, the sensors were not only higher quality, but they were faster to the point where if the world doesn't change too much between each frame, then you can write a simpler algorithm to do tracking and reconstruction. Okay, so there was just this massive revolution in geometry that's happened sort of alongside the deep learning revolution. And interestingly, they've come together. So now, there's people baking in geometric priors into neural networks and the like. Okay, so it started with sensors that were thinking, maybe autonomous driving related. So you see a Velodyne. Actually, Spot has a Velodyne you can stick on top of it. It's still a relevant sensor today. These are LiDARs, laser being shot out and bouncing back and estimating the distance from each point of light to the target. Okay, and some of these reconstructions are just absolutely amazing. You'll see an autonomous car driving through a city street, and hundreds of yards into the future, you can see like a cat walking around a bush or something like this. It's just incredible what kind of resolution and range that those sensors have. That's like the Luminar in particular, 500-meter range. Crazy, okay? Indoors, though, you'll tend to see a different type of laser scanner. These Hakuyus were very, very popular, are still very, very popular for sort of indoor navigation, where the lighting conditions are not as severe, the payloads can be a lot smaller, the energy budget is maybe smaller, okay? But LiDAR is definitely one of the tools that sort of enabled this sort of revolution. But alongside that were cameras that didn't only return depth, lists of numbers that are just the depth, but coupled RGB, red, green, blue, color images with depth images. And you get those in a handful of different ways. Some of them are actually just using stereo processing of the of the depth of the RGB images. So if you take an image with your right eye and an image with your left eye, and you know the relative position of your eyes, you can do some quick stereo matching that says, well, this block over here looks a lot like the blocks over here, and therefore the depth of those pixels must be at a certain range. Okay. People do that now on FPGAs, for instance, on specialized hardware, so that you can package it nicely into a block that basically is just outputting both an image and a depth. This is the Carnegie Multisense is actually the head that we carried around in Atlas the entire time. You'll see Bumblebee, point grays from Bumblebee. There's a lot of systems that are doing like that. Okay, let me go through the first round first. Okay, another line of tools like this, the Kinect sensor was a big deal when that came out. Not only because it worked very well, but because it was so inexpensive, right? So somehow the home entertainment gaming world kind of revolutionized robotics by building a sensor that we needed. Okay, that was fantastic. The first version of Kinect worked with structured light. So it's actually about as simple. I mean, this was an idea for decades and decades, okay? But it became practical with the Microsoft Kinect, where you actually just project patterns. The patterns will deform on the object. You can back out from the geometry something about the depth. Xgeon, there's a bunch of different hardware manufacturers that built structured light-based depth cameras. The ones that I showed you here, like the 415 we'll talk the most about, is actually projected texture stereo, okay? So the problem with just taking two camera images is if you're looking at a white wall, for instance, there's nothing to compare and contrast between the two images. Okay, so if you project in infrared, for instance, that something that will just put a little bit of a pattern, then you can, even in low contrast situations, you can get depth to come back out. Okay, one of the reasons that's nice compared to some of the other options, like the time of flight I'll show you next, is that these cameras can work even if they're looking at the same scene, and they won't interfere with each other. Right? So sometimes some of these cameras, if they're sending out pings or something like this, they can actually actively interfere with each other unless you synchronize them very, very carefully. One of the projected texture, you can just point them and forget. Okay. And then these days, there really is a massive movement that was powered by deep learning, which is you can just go straight from RGB. Okay, so a lot of times, even if you only have a cell phone camera and you don't have it, actually the cell phone cameras have depth sensors, a lot of them, true depth on the iPhone, for instance. Okay, a lot of times you can actually build beautiful 3D models even from a single camera. You don't even need the stereo pair. There's enough cues, of course, from movement and other things, but there's also there's additional information that can be available if you've read everything on the internet. That's not what's happening in this particular one. This is a neural radiance field we'll talk about later, but just to say, this was one of the first videos of the neural radiance field showing that just from taking camera images, you could stitch together into something that could project and generate new images from new viewing angles. And there's also lines of work in monocular depth that, for instance, will just have a very clever thing to do, for instance, is to drive a car around with two cameras on it, and then just use the second camera to use stereo matching from there, but just learn a model from the single camera to the depth. And then, when it's time to make 100 million of them because you're going to make it to a product, you just take away that extra camera and just use the learned mapping from image to depth. Right? So monocular depth is a surprisingly effective technology now. Okay, now is a good time if you have a question or anything. Yeah. I don't actually know what's in the iPad. So I know that there's a true depth sensor here. If you look, at the back of these, they're projecting something here, and they have the ability to do. You do have a depth camera on your iPhone. I don't have an iPad to look at. Yeah. Okay, so the second question was about the LiDAR on spot. So typically the Velodynes on a car or on spot. The spot I brought did not have a Velodyne on it. It just had the surround cameras. But yes, typically those are scanning LiDARs, and you have to do some careful work to think about blurring from fast motions and timing it with the spinning laser. That's true. I think spot's pretty good. Yeah. Okay, so oh yes, please. Yes. So the question is, I mentioned FPGA and the Carnegie head. Yes, I think that basically, if you're doing block matching stereo, that's the simplest algorithm, and they're doing more than that in those heads. But that's I think the essence of the hardness in the computation is that you're doing a relatively simple computation, taking an 8x8 block of pixels, comparing it to another 8x8 block of pixels. But you have to do that for all possible pairs in a row, for instance, like this. So it's a very trivially parallelized operation. And in order to get operating at full frame rates, I mean, computers have gotten faster and faster, but it's just a beautiful solution for specialized hardware. Yes. Yeah. Depends on the technology. So, so like NERF out of the box, the neural radiance fields, don't have scale unless you do some work a priori to tell them about the relative poses. So you can run a different geometry processing algorithm first. Most of the projected texture or anything that's projecting light actively does have absolute scale. Yeah. They do have maximum range and minimum range. So a lot of them are actually, it can be frustrating to use them. You put a beautiful sensor on your wrist, and then you realize that the minimum range of like the D415 is 0.3 meters or something like that. So, when you're getting close to the object, that camera becomes blind in the last 30 centimeters, for instance. Okay. Alongside this, many sources of camera input, we also have a lot of different ways to store that data when it comes in. Lots of different 3D representations. A bit like we talked about representations of rotation, there's just a handful of different formats, for instance, and some of them are good for some type of computation, and some are good for the other. And you should expect to convert back and forth between them and figure out which one's best for particular sources. So the image that you get directly out of a depth camera that has RGB, you think of that as an RGB plus D image. So it would have 4 channels. The first 3 are color values. The last one is just the depth at every pixel. That's kind of the output of these cameras by default. Okay, so that's 1 depth per pixel, right? We're going to take those RGB images, which is a perfectly good representation, and convert them into colored point clouds. Okay. So while this is a 4 by size of the image representation, a point cloud is a list of points in 3D, possibly annotated with color values or normals or other attributes. If you compare that to some of the ones you might have seen from a graphics software or graphics course, you'll see things like triangle meshes. Or there's volumetric meshes. Triangle meshes are surface meshes. And you can have volumetric meshes in addition to surface meshes. You can think about sine distance functions as a representation. increasingly now, people are choosing to store those in neural networks. So NERF, this is the neural radiance fields I was mentioning before. Is almost a signed distance function. We'll get to the nuances of that when we get closer. Okay, but this would be, I mean, we're gonna go into each of these when it becomes most relevant. But I want to just sort of get the landscape out here first. Okay, you can also see voxel-based representations. Sometimes occupancy grids. Okay, there's lots of different ways to represent 3D data like this. Okay, some of the algorithms will really more naturally fit with one versus the other, and most of the time you can go back and forth. Yeah.
Sorry, maybe some question about in the RGB, as you mentioned, like not the same as big as the RGB. So
Oh no, I think by default the depth channel is the same size as the RGB channel.
yes, but like the sampling it was the same dimensionality, or are the depth channels or are
The depth always will give you some, will have some minimum range, some maximum range, and some resolution inside that range, of course. But you should think of it as an image that has, for every pixel, a depth specified. So in that sense, the resolution is the same, yeah? Yep, yep, you should think of every pixel being labeled, yes. So there's a lot of algorithms. In fact, the one we'll talk about today doesn't use color to start, okay? But you can potentially do better if you also include color values. So, some algorithms will only use the D part. In fact, I would say many of the algorithms before deep learning really came in would have only very limited use of the RGB values, because RGB, I mean, computer vision is hard. Let's just take a second to remember why computer vision is hard, right? So if I take two slightly different images, okay, of a similar scene, if the lighting changes at all, right, the color values are going to be wildly different for pixels that correspond to the same point in real space. Or if I take the same object and put it in two different rooms, right, the same point on the same object is going to come up with very different color values. Okay, but having said that, if you were to, I remember the time when I was with my students and we were enjoying how well RGB techniques were starting to work. And I said, okay, today, if you were to pick, if someone could only give you depth or only give you RGB, what would you pick? And nowadays, it's RGB all the way. RGB is so much more informative. There's so many things that you can't see through a depth camera that you can see in RGB. And humans, of course, are very, very good at that. So I think if you have a method that's only limited using depth, it's probably limited. It's probably not the state of the art. Okay. All right. So let's dig in to sort of this part of the pipeline first. Go from RGB to point cloud and start seeing the connections between the geometry of these camera representations and the geometry of spatial transforms and the like, and how do we write optimization problems over them. Okay. Maybe I'll do it over here. So this is maybe not a super popular view here, but you could argue that perception is just a hard kinematics problem. At least the first version of perception we're going to do today. Okay, it's certainly a controls problem, but even before that, we're going to think of perception today as a kinematics problem. What do I mean by that? Okay, so let me say I've got an object in space. Okay, so I'll do 2D objects here because my artistic abilities are limiting in that way. Okay, so let's say I have an object in space, and it's got some coordinate system, some canonical coordinate system. I'll say this is my coordinate frame O, and this will be the X, and this will be the Y axis, okay? And I'm going to say the first thing I want to do is represent this geometry. I could represent it as a series of bases, for instance. That would be most similar to the triangle mesh. In 2D, it would just be line segments, okay? But instead, I'm going to use a point cloud representation of that object, okay? So I want to represent this object with a series of points on the boundary. They're going to be points in now, for my example here, a 2D space, and they're going to be written in the coordinate system of the object. Okay, so I'll call those points the model points. Sort of my model of the object, and I'll write them as points, right? P for point here. If I have model point I here, and I'll say that my model exists in the object's frame. Okay, position of the object of each point in the object frame. Okay, now I have a camera that's kicking out some other points. Hopefully they're relatively similar, okay? Similarly spaced, but maybe I have something that is coming out like this, okay? By the way, you rarely get all the points from a camera, but we'll assume that for just a start. And I'll call these my scene points. SI for scene. And what I get out of my camera is the scene points in the camera frame. And let's say I took great care when I mounted my camera. So maybe we can say that the location of the camera in the world is known. If it's bolted to your hand or something like that, that could be also just a forward kinematics problem to figure out where the location of the camera is. Yeah? It can be, yeah, absolutely. If it's bolted to the robot, then you would definitely be, as a function of the joint positions, right? So far, this is just a pose, not a rotation, no, not a velocity. Okay. So the challenge, the goal of perception in this case, is to figure out the transform of the object in the world. Right? You have a lot of the pieces. We have points in the world. We have camera points in the world, model points and scene points, and then we have the camera's location. Yeah?
So you assume these points are in the 3D world. So they are not like really the kind of form or even like basic point that you see on a 3D camera.
Great, great. Yes. So so the point cloud resolution, so that's a really good question. So the question was, the camera, I think of a camera image as giving me points in a 2D picture, right? But if I have a depth channel inside that, then it's the first step that I should have said is I'm going to take those 2D points in the camera and I'm going to project them into a 3D point, right? By just applying in my camera frame, that's easy. I just say that it's at some depth in the immediate frame. Now, there's a couple steps that are involved in that. So first of all, there's like intrinsics in the camera. You have to take out any distortion from the lens or something like this. But this is something we know a lot about. It's still a pain, but it's something we know a lot about. And then the other thing is the extrinsics, which is to take those points in the camera frame and bring it into the world frame, and that would be this XWC. That's the camera extrinsics. Okay. Good, but all those are quite doable to go from the 2D picture with a depth channel into a 3D point. Yeah. Okay, but there's another step. Yeah, go ahead. So let's say this is exactly the same object, right? That my model was perfect, right? So and that my sensor had zero noise. Okay, there's still things that can get in the way, right? Which is that like those points might have been sampled in different places along the, there's reasons why that's almost never going to be perfect. But as a toy problem to start, I'm actually going to say let's consider the case where we've just taken the model points and someone translated them through an unknown transform, and we're going to try to get that back. Okay, that's the easy case, and we'll look at the harder case where there's noise and outliers and other things in between. Great question. Okay, there's another thing that we have to assume that we will assume to get started. Okay, these are all just yellow dots. Okay, and these are all just yellow dots, and your incredible brain knows how to map. Knows that this yellow dot probably corresponds to that yellow dot, okay? But if it's just a list of numbers on the computer, that mapping, the correspondence it's called, between those points and this points is not given. And in general, it has to be acquired by some sort of logic, right? You have to figure out which of these, if you just have a pile of points over here and a pile of points over here, figuring out those correspondences is a massive part of the problem. Okay, but let's just start by assuming that someone said, that the ith point here matches the ith point over here. And we'll solve the second part of that problem in a second. Yeah? So let's say I had a CAD model. I could take these points directly from the CAD model. So if that's helpful, that's why I'm using the word model. Sometimes the way you get it is you put your object down in a nice situation and you get one scan and then you use that as your model for finding it in other things. Okay, but think of this as like you've got a CAD model and then this is the real object out in the world that I got returns from. That's the scene. Okay, so step one, we'll assume known correspondences. Sometimes that word, I feel like I forget to define it, but just the mapping, I would define it in symbols in a minute, but the mapping from those points to these points are the correspondences, right? Okay, so in that case, you can sort of see that we have a nice little kinematics problem, an optimization problem. We know that the ith point of the model should correspond with the zero MI. That's the model in object frame mapped to the world frame, should correspond to in the simple, exactly one-to-one correspondence problem. These are the obvious kinematic equations, okay? And in this, these are all known, or given, and this is the unknown. question becomes, how do I extract the pose given a list of, for all I, a list of many correspondences? Now, if we dig in just a little bit to the pose representation, you remember from our spatial transforms that doing this is equivalent to both the translation plus the rotation. Okay. I'm leaving off the W for my shorthand, but the W is everywhere. Okay, so really, if the unknowns are both the translation inside there and the rotation. The rotation, you'll remember we have lots of choices about how to represent it. This is always 3 numbers, basically, in 3D. In 2D, it'd be the 2 numbers. Here we have many different ways we could possibly represent the 3D rotations. But somehow we need to search over these. Okay, and that's the question. So solving this is actually an inverse kinematics problem, right? We're trying to figure out, given the data, the points in space, we're trying to back out the orientations and rotations. So this is an inverse kinematics problem. Now let's stop and think for a second here. So last time we didn't actually do inverse kinematics, we did differential inverse kinematics. I said inverse kinematics is harder. We're going to defer that till later. But this time we're going to go directly. I haven't written any differential kinematics yet. I've just written a kinematics problem. So this is like, the positions and orientations inside here is like our generalized coordinates that we're trying to back out. So what is the difference? Why did I advocate immediately diff ik for moving the arm around? But I'm saying we're going to have to solve the full inverse kinematics problem for this one. Yeah? I think that's right. So he says you don't have the ground truth, right? So effectively, the magic that happens in the robot case is that you know the initial conditions, and you want to change those initial conditions. So you have an initial Q, and you're making small changes to that. So you have a place to linearize around. Okay. In perception, at least once you have to wake up and figure out where the objects are. You don't have an initial, unless someone gives you a good initial guess, then you could be in the land of differential kinematics, inverse kinematics. Okay, but we're saying at least once you have to figure out the hard problem, find the needle in the haystack potentially. Okay. Now, once you solve that once, I actually would advocate differential inverse kinematics if you wanted to track, for instance. If you want to do real-time tracking, then by all means you should be thinking about gradients and the like. Okay. But the one-time problem is a little bit, it must be solved, I guess, in the perception case. Fortunately, this is not some complicated chain of equations that can lead to lots of nonlinearities and local minima and stuff. This is about the simplest inverse kinematics problem we could have to solve, and we're going to see it has beautiful structure and good solutions. Okay? Okay, so let's start, we get to pick a rotation representation. Now, the derivation I'll do would go through fine for, at least for quaternions, and we're going to do rotation matrices here, just because I think it's a little bit, it's obviously a linear equation in a 3x3 matrix here, so it's just a little easier on the board. So let's say, even though this is my spatial algebra rotation, we're going to represent this with 3x3 matrices for the purpose of this. And this is 3x1 numbers. Yes, do you have a question? So, I've got a mug here. At least once I'm going to say, I'm going to build a CAD model or whatever, and I'm going to pick an origin of my CAD system, and I'm going to just define an object-relevant model of this. So I think that is the natural, like if you think about what you would have to do to build a model and write some coordinate system, the natural thing would be to attach your coordinate system to the object itself. Okay? And then the question of then is of where it is in space becomes where is that object in space? That's the second transform. I think. Yep. Yep. So pick the bottom corner. You know, it's just like if you were in SolidWorks and you were, you know, you have to just start drawing lines. You got to pick a 0, 0 somewhere. Okay? And all of your points are sort of relative to that 0, 0. It doesn't matter if you put it in the middle. It doesn't put it in the middle or in the bottom corner. But it's just the frame of reference that you're going to define those points relative to each other. Thank you. That's a good question. Okay, so now to solve this problem, we want to back out those 9 plus 3 numbers, 12 numbers, in order to make those equations match. Okay? A little annoying that I picked a divider right there. Let me slide that out. Okay, that's the game. How do we do it? So first of all, do you see, even though it doesn't look quite in the normal way, but do you see that's just a linear equation, right? So this is, you should see that this is like AX is approximately equal to B, right? Except in this case, the X would be my three positions, and then the 12 rotation coordinates all stacked in one line. If I just flatten those into one vector. The A has a bunch of stuff about the PMI in here, flipped around a little bit and shifted, okay? And this has got the PSI over here inside that, okay? But it really is just, you could just rewrite that if I flatten that out into a big A matrix, that's your data matrix, big B matrix, okay? And you're trying to solve a least squares problem to back that out. Almost. Almost. Yes? So this is the scene points, in the, I guess in the camera. It also is going to have inside it the X WC, which is, I guess, given. Right? In this bright pink thing on the top, that's the right-hand side. Yeah. And then the rest of it is decision variables, which are just multiplied by the PM. So if I just tried to solve AX equal to B, if I just tried to take an A inverse, what's wrong with that, right? If I have any number of, so you need some number of points. We'll ask you on the P set exactly how many points you need for that to be well defined, okay? You need some number of points for this to have a unique solution, okay? But most of the time, you're going to be in a situation where you have many points, many more than 12 points, let's say. Well, if each point contributes 3 things, so many more than 4 points, hopefully. If you're at the 4-point room, find another camera or something, right? Okay. So if solving that with exact equality would be very brittle for all the reasons we brought up a minute ago, right? If there's any noise, if you sampled slightly different points on the surface, just because of the position of your camera or something like that, that's not going to be a good way to go. So we're going to solve this again in the least squares sense. Yeah? Yeah, I was thinking about that myself. Oh, look at that. Wow. It used to be like I had options 1 through 32, but now it actually just says chalkboard and center light, turn on. Oh, no. That's good. They just upgraded that this year. Okay, that was way too easy. I should have done that before. Yeah. I'm sorry? This is I'm using this as an abstract. So when I see this, I think of a standard linear algebra problem, where typically in linear algebra, when people write this, they'll use A and B matrix. And what I was trying to convey is that the problem we have with different variables that are rooted in geometry could be interpreted as our standard AX equals B, where the A matrix is populated with the data from PM, okay? And the B matrix is populated from PSI. Yeah.
Is this going to give you a valid rotation matrix? Because
That's exactly the, yeah, so you got it right. So the reason I said almost, he says, is this going to give you a valid rotation matrix, right? So what I really want to write in an optimization world is I want to minimize the difference between the right and the left-hand side. This is basically my AX minus B, okay? But I'll say P plus R POMI minus PSI, that's already rotated into the world frame, okay? Sum over I. I'm going to minimize this over PR. That's almost what I want to say. Okay, that's like the least squares version of that fitting. But there's one important detail, which is that not all 9 numbers, you can't pick arbitrary 9 numbers and get a valid rotation matrix. Okay, so what I'll do is I'll write in here, R has to be part of SO3 as a constraint. This is the special orthogonal group 3, okay? And you're going to understand it completely. It just says it's a valid rotation matrix. One way to write that is with additional constraints on the optimization problem. So I can write this, in the shorthand, but in order to implement that, what I would actually do is write the things that define a valid rotation matrix. First of all, R transpose has to be R inverse. That's one constraint that makes a valid rotation matrix. And the other one is that the determinant of R has to be positive 1. So this is the optimization problem we're working on. Yes?
Second constraint necessary because doesn't transpose everything determinant.
That's a good question. So it turns out that this constraint by itself ensures that the determinant is either +1 or -1. But the -1 case can get you. And that would be called an improper rotation, which is a rotation plus a reflection. So if you want to stay with the proper rotations, you need the extra constraint. That's a good question. In practice, we will drop this and then check for reflections afterwards and flip it back, because this is an ugly constraint in general. In fact, if you think about this, so this we said is, if in the decision variables, the inside of this is a linear function, which means the squared is a quadratic function. So you should be thinking I've got, a quadratic bowl like this. That's a good case. What are these in terms of the constraints? I told you quadratic programming is beautiful if you have, but it's defined when you have linear constraints. Are these constraints linear? Right? This is not a linear constraint. It's also a quadratic constraint. The way you could see that is you multiply by both sides and you say R times R transpose equals I would be an equivalent writing of that. And so the decision variables have to be 0 or 1 to make all of the 9 elements match. Okay, but those are each of those, the entries in this matrix is a squared of the original decision variables. Okay, so this is a quadratic constraint. This constraint turns out to be cubic in the 3x3 matrices. In 2x2 matrices, it's actually the same as it's a quadratic again. Okay, but that can be in general cubic. So those are less good, but it turns out that we have really, really good solutions to this one. This is like one potentially ugly, hard class of optimization problems where this one we nail it. Okay. Let's actually do the 2D example. I think it's useful to understand the optimization landscape. Right? What are we setting our code up to have to solve? Okay, so let's say we're going to do the 2x2 version of it. So in that case, a 2x2 rotation matrix, you'll often see it. It's cosine theta, negative sine theta, cos theta. We could try to search directly for theta. But to keep our analogy to the 3D case, what I'm going to instead do is I'm going to just name a variable. I'll call it, what did I call it? A for cosine theta. So B for sine theta. And also I'll parameterize my matrix as A, negative B, B, A. Again, I'm going to search over A and B. This is a trick that you can't quite do in, so in 3D, if I would have had to, I could have done A, B, C, D, for instance, like this. It just happens that in 2D, I know there's not enough degrees of freedom. I know that I can solve away C and D, so I haven't done that. But in 3D, you don't get that same luxury. That was your question, was it? Or? Okay, we'll come back to it when it makes sense then, okay? All right, so let's just multiply this out. So what does R times R transpose equal I look like? Well, that looks like A negative B, B, A, times the transpose of that, A negative B, B, A. And that implies, in order for this to equal 1, 0, 0, 1, that implies A squared plus B squared has to equal 1. And it says that AB minus BA has to equal 0. Okay, so that's two quadratic constraints that define the rotation matrix being a valid rotation. Okay, and this is the same thing is happening in 3D, same type of thing, but you just have more equations flying around. It happens if you wanted to say that the determinant of this equals positive 1. In this case, it's the same as this, right? This is also the determinant of R equals plus 1. And that's because I took out the improper rotations by my parameterization, roughly. Okay, so yes? Yep. Sorry. That was just me spelling it out, but you're right. That's trivially true. Yep. Also because I did the change of variables. Okay, so I made a animation or a visualization of this, okay? So what I want you to think of is an objective that's a quadratic bowl and a constraint that is this quadratic constraint. So what does that look like? It went out of order, but here it is. Okay, this is what it looks like. Okay, so I took a few points and I made my quadratic objective, and I took my points and I just rotated them. I'm just trying to bring it back. So I can actually dynamically rotate what those points are. Okay, and it's moving around, and my goal is to find the bottom of the quadratic bowl, but it has to be on this constraint. So if you look down from the top, this is the unit circle constraint, which looks like a cylinder. I mean, it projected up, okay? So I have to find the lowest point on the parabola that intersects with the red constraint. And it turns out, in the case where there's no noise, the minimum is always going to be on the manifold, right? Because the best rotation that you could find is going to be a valid rotation. Okay, so in this case, it's actually the good case. Now, as soon as you add noise, that the parabola could move off the unit circle, and you're going to need to project it back onto the unit circle. That's the fundamental geometry of this problem. It's a very famous problem. It's the point correspondence problem, the WABA problem. It comes up in all kinds of fields. It's a famous problem of this. Solve a quadratic objective onto the unit circle, or the SO3 constraints. Okay. Interestingly, yeah, go ahead. It's only a little bit hard. So it is harder to do. Basically, I don't know that, I don't have the simple relationship to just know that this is negative sine theta, so I would have to use 9 numbers instead of, I just used 2 numbers here. In 3 by 3, I'll have A, B, C, D, E, F, right? And then the R transpose R is still quadratic. The determinant is cubic for a 3 by 3 matrix. Yeah. Okay, but the geometry is roughly the same. Yeah. Yes. That's this constraint and the determinant constraint. So, yeah. Okay. Interestingly, let me just get one more thing in, and then, so interestingly, we could have parameterized the whole thing directly with theta. Okay, that's only one variable. In 2D, of course. In 3D, we'd pick quaternions, or we'd pick one of the other representations. In this case, it's maybe illustrative to see that if we just did it in terms of theta, what does that cost function look like? I threw that on a plot too. No, but okay. And it is similarly beautiful and good. Okay, so now there's no constraints. If I were to just parameterize it with theta, then I would always get a valid rotation out. I don't need this. So I could just write my objective. But the objective is no longer quadratic. It's a non-convex objective. It's got sines and cosines in the middle of it. And the sines and cosines multiplied out, you got cosine squared, whatever, to the second power, gives you a cost landscape that looks like this. And if I move my theta that rotated the two relative to each other, then the minimum moves correspondingly. Luckily, all of the minima are good in this case. They're all just 2 pi off. So just, similarly, this is a good optimization. If I start with an initial guess and I go down, then I'm always going to find a good answer in the no noise case. These things are going to behave differently, not only when you have noise, but also when you have additional constraints. Like, for instance, if you don't want your object to penetrate the world or something like this, that becomes a harder constraint, and we'll see the differences between those representations more. Yeah? In the 2 by 2 case, it is quadratic. In the 3 by 3, it's not quadratic. But what we're going to do is ignore it. The rotation matrix is sufficient to get determinant plus or minus 1. We're going to solve. If our determinant was minus 1, then we're going to multiply by a -1 in one of the. Yeah. So basically, it's whether you have a right-handed rule or a left-handed rule. If you end up with a left-handed rule, you flip it back to a right-handed rule and you call it a day. Yeah. So that's how we get around that one. But you're right, it's cubic. Okay, so that was just searching for rotations. I left out in this simple example, I left out the positions. But one of the most important insights I want you to take away today is that actually you can separate solving rotations from solving for the translations. Okay, why is that? So registering the points, the key insight, and we already had it in the first lecture about spatial transforms. Remember, I made you, I did a check yourself kind of thing, saying the position of B relative to A only depends on the rotation between those two frames, not on the position, because it's already a vector. The base of that vector is rooted in the coordinate system. So the relative positions of 2 points only depends on the rotations. So the trick is, if you just try to fit every point by itself, then you have to solve for the translation and rotation separately. But if you just take the difference between 2 points, that quantity does not depend on the translation of the object. You could take an object, I don't know, in building 32 or an object here, okay? And the absolute translation does not affect the relative points, only the orientation. So the trick is you subtract out some nominal point in the middle of your point cloud from all your points. You solve for the rotations, and then at the end, now that you know the rotations, you can easily figure out the positions. Okay? You can solve for the rotations separately. You guys didn't look like you got that. I mean, I'm not trying to, but you didn't look as happy as a you know, on average, let's just say. Yeah? Yes? That is true. That is true. So you said it almost right, and I have to re-say it for the people on the video. So we're going to take the model point cloud. We'll find the centroid of the model point cloud, and write all of the model points relative to the model's centroid. And I'll take all of those scene points. I'll take the scene centroid and write all of theirs relative to the scene centroid. And then I'm going to try to take those relative coordinates and rotate them until they match. And now I have an easy problem to just snap the positions into alignment. So it's a two-step process. Yes? So the question is why at an arbitrary point? So the key insight is that it's the relative points that match. It turns out there is a kind of a natural point to pick, which is the centroid, because then it actually just drops right out of the equations in a beautiful way. Yeah. Yeah.
Is the centroid the average of the surface?
It's the average of the points. It's literally the average of the data points. Yeah. Yes. In 3D also. It's only rotations that affects the relative points. If you have this point relative to this point, then the only thing that changes that number, changing the coordinate system doesn't, the location of the coordinate system does not change the relative number. It's only the rotations. In 3D it works fine. Yeah. Okay, so quick quiz. So what happens if you have a symmetric object, right? So I drew one sort of intentionally that had an asymmetry there. What if it was a box?
It's going to be impossible to know.
So she says it's impossible to know. If it was four-way symmetric in an actual box, then it's impossible to know. So you're right, of course. But the thing, I just want to make sure it's clear that so far I've assumed known correspondences. So in the case of known correspondences, there is no symmetry. It cannot be, right? It's someone told me that this point corresponds to that face, and there's always a unique solution, right? And the reason that's sort of maybe puzzling is I'm showing you these plots that look like they have a unique solution, even in the case of something that has symmetries. And the reason for that, it's not a trick. That function doesn't change if your object suddenly becomes symmetric. It's because it's the known correspondences case. Okay, let me keep moving a little bit. So I want to get through a couple things. All right, and we'll ask you a couple questions about uniqueness and the like on the problems. Okay, is that basic idea clear? So if someone gives me the correspondences, then I have a very good algorithm, which is just solving this. That can find the optimal solution. In fact, even the solving the quadratic thing, projecting onto the unit circle, you don't have to just solve and then project. You actually can solve it beautifully, and it turns out the solution is given by the singular value decomposition. Okay, so the WABA problem is famously solved by the singular value decomposition. If you have extra constraints, then you're going to use extra machinery. Typically, a very powerful way to write that is as a semi-definite program, which we'll get to later. Okay, but these kind of quadratic constraints are a particularly nice case of a semi-definite program. Okay, but in the unconstrained case, or only this constraint, this is like the SVD. If you know the basic picture of the geometry of SVD, right? It's about finding the coordinate. You warp it to the circle, you rotate it, and then you warp it back. Okay, well, that warping to the circle is exactly the warping that happens of projecting onto the unit circle. Okay, so it turns out to be exactly related to the SVD. Okay, so equipped with that, we now have the most important algorithm for sort of geometric perception, which is the iterative closest point. The biggest assumption we made so far was this known correspondence, right? Someone told me the relative correspondences. If I instead have to solve for the correspondences, then I have an extra work to do. And just to give my notation, let's define a correspondence vector, okay? So I'll use a correspondence vector C. One for, it's the length of num points times 1, okay? So num points by 1 vector. And the ith element takes an integer value. And I'll say the ith element is an integer j if point si corresponds to model point mj. And now I was careful to choose that, so it doesn't have to be a one-to-one mapping, right? I'm going to try to power through a little bit more. So it doesn't have to be a one-to-one mapping. There could be model points that don't have a corresponding scene point, which is important because oftentimes if you have a camera, you're just looking at one side. You're not going to have scene points all the way around the object, okay? But we're saying that every scene point corresponds to a model. There's other choices people sometimes make where you assume that every model goes to a scene and that all of them have implications. But in this, we're going to choose it like this, okay? I could then just write my optimization. I'm going to search over x using that notation minus p si squared. But now I have to search, I have to find both ci, which is this discrete thing, right? This is it's a function on the elements of 1 to num model points. That's the set that lives in. So it's kind of a weird thing to optimize over. And x in SE3. So how am I going to optimize that? Right? It looks like kind of a quadratic objective, but with a combinatorial aspect of it, of trying to figure out all these correspondences simultaneously. And you can do that. We've had a paper that does that kind of thing, where we're trying to do the combinatorial search at the same time as the continuous search. But it's an expensive optimization. So the ICP algorithm famously does it by splitting it into 2 parts. In many optimizations, kind of like this, it's often the case that if you fix one set of variables, then the optimization is easy. Fix another set of variables, the other optimization is easy, and then you end up with natural algorithms that alternate between the 2 optimization problems. And that's exactly what we'll do here. Because if the correspondences are known, then the optimization is exactly what we did a minute ago. That's the point registration with known correspondences, and it has a beautiful solution. And then the other side of it is if the transform is known, then finding the corresponding points is just a nearest neighbor problem. Okay? So if we have an initial guess for x. Then we can find, we'll take step 1, solve the nearest neighbor problem. So C, our new CI, is going to just be the, we can just try all the possible correspondences, basically. I'm going to say x p o n j argmin over j minus psi squared. So for a small point cloud, you can just literally try all the possible correspondences for this. When x is known, you can just measure the distance and take the smallest one. Okay. When it gets bigger, you start using efficient nearest neighbor data structures like KD trees and stuff like that. Okay. But this is a fast nearest neighbor query. And then the second step is given correspondences, solve for x. And then you just repeat until convergence. Okay? So let's see what that looks like. Try to not stand in the middle of your right here. Okay, so this is the kind of plot I'm going to show you here. So this was the known correspondence one. I picked a lovely salmon color for the random object with random points in 2D and known points. And then I rotated it and translated it by some random quantities and got my blue scene points. In the first step, we have a known correspondence problem, and the registration just works exactly. Okay, that's the known correspondence version. Now, if I take another example here with my scene, my model points and my scene points, if I start the ICP algorithm, then I think I can just step through. Yeah, here we go. Okay, the first thing I do is I solve that, given that initial guess, which was a bad initial guess. This is the initial guess here. I just compute the nearest neighbors. For every scene point, I find the nearest point. Okay, and then given those correspondences, I try to solve for the new optimization. And it doesn't do very well because my correspondences were all wrong. But the hope is that it gets you closer. Okay, and then I get a new chance at my correspondences. And many times, this converges beautifully in a small number of alternations because at some point your correspondences are correct and you snap right into place. Yeah. Yes. So just like you can separate translation and rotation, scaling can be separated too. And the trick is, so just like the observation is that the relative positions only depend on rotations, it turns out the difference of distances only depends on scale. So if you play that trick one more time, you get something that only depends on scale. So you can fit scale first, and then fit rotations, and then fit translations. I actually cite that in the notes, because I think that's part of the story. Yeah?
Translation wasn't that much of a rotation. What would have happened if it was, let's say, turning around and will it get stuck in local minima?
Yes. Good. So this algorithm can absolutely get stuck in local minima. There's in the code you can play with. It's just random. So the fact that it's mostly translation, it's probably because I wanted one that fits on the slide, but I didn't think of it that way. Now I feel like I picked a bad example. But yeah. But it absolutely can get stuck in local minima. Yes. If you pick the wrong correspondences, you make not enough change. You could get the same wrong correspondences back, and that will never leave, right? So there are many ways, and we're going to talk about those more next time, but there are many ways. You can try random initializations of correspondences, but you can also, there are more robust methods that can try to avoid some of those local minima. Yeah. So, and we're going to talk about noise also next time. It's a fairly subtle question, and I had a slide I blew past real quick, but just to show you some, like, real world noise is extremely structured. So if you think about noise as like adding Gaussian values to all of those values independently, that's not the way cameras have noise. Cameras tend to have, like, this is the actual depth image, and this is like the depth image you get out of a camera. They have dropouts, like pixels that are just missing in the middle. They will have swaths of, like, a shiny material might have very noisy things, and a flat material could not. So the answer to your question requires thinking a little bit about the types of noise. Yeah. Yep. You just alternate back and forth between. When X is fixed, the problem is easy. It's nearest neighbors. When the correspondences are fixed, then the problem is easy. It's this lava problem. That's true. You're solving many optimization problems in the loop. This one is so easy that it becomes an SVD. It's a call to SVD, so I wouldn't even call it an optimization problem in the implementation. It's very fast, even for very big point clouds. But yes, it is alternating between those. And I'll take it home with one more example here. So yeah, I've got lots of examples of real noisy things, but you're going to play with the bunny, because everybody who ever does ICP makes the Stanford bunny snap into alignment with another Stanford bunny. That's just like, early in computer graphics, the Stanford bunny sort of did a winner-take-all thing, and it just won out, and everybody uses the Stanford bunny, okay? So you'll do that on your problem set. But just to show you, even in the examples I showed you of, like, the loading a dishwasher, for instance, if you watch carefully at what happens, so there was a perception system that tried to figure out where the mug was to begin with, okay? But as the robot moves, even in this sort of state-of-the-art perception system, okay, state-of-the-art a few years ago, I guess, but watch this. That was running ICP. I mean, that wasn't the ICP updates, but it actually, when it goes there, it has a model of the mug back in the day, okay, and it actually tried to align the model of the mug before going into to close the difference between the faraway camera's rough estimate of where the mugs were and actually making the pick. And people still do that today. Leslie and Tomas, we were in a meeting with Leslie and Tomas the other day, and they're like, we're going to do ICP for this. And the young students were like, okay, that's kind of old school, but it still works. Like, it still works really well. Yeah. Yep. So this is part one. Part two is, like, how do you do more robust versions of this with partial views and outliers and noise? Yep. So we're going to talk about that next time. Good. I'll answer. You can come on up afterwards. Yeah. Thank you.